All right, so describe each pattern, then write out the next three numbers. So 4, 14, 24, 34, 44. Looks like each time I'm adding 10 to the number. So this would make it arithmetic, where the common difference is 10. So if I continue on the pattern, 4, 14, 24, 34, 44, it would be 54, then 64, then 74. B is not arithmetic and it's not geometric, but there is a pattern in that each number looks like I have 1 1, then 2 1s, then 3 1s, and 4 1s. So I'm adding an extra 1 each time. So the next one should have 5 1s to it, and then 6 1s, and then 7 1s. So the last number there is 1,111,111. C, you can look at it a couple ways. 1, 4, 9, 16, 25. If you think about this, it's not arithmetic, but notice if I go from 1 to 4, I'm adding 3. And then from 4 to 9, I'm adding 5. 9 to 16, I would have to add 7. To get from 16 to 25, I would have to add 9. So there's an arithmetic sequence with the addition of the numbers. So it's the sequence itself is not arithmetic, but there is an arithmetic sequence embedded inside of it. And the next one would be add 11. That would give me at 36. I would add 13. That would put me at 49. And then I would add 15. And that would put me at 964. Another way to think of this is if you know your square numbers, this is 1 squared, then 2 squared, then 3 squared, 4 squared, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64. So there's two ways of looking at this that both give you the same answer. And this last one is a little bizarre, but let's see if we can figure this out. 12, 15, 51, 54, 45, 48, 84, 87, 78, 81, 18. What I noticed right away is that from 15 to 51, 54 to 45, you can see that those, the digits have been reversed. So the 1 5 to the 5 1, 5 4 to 4 5, 4 8 to 8 4, 8 7 7 8. So it looks like there's sort of some number reversals here. But what about from one of those pairs to the next pair? So if I want to get from 12 to 15, I would add 3. Let's see if that holds up. 51 to 54 would be add 3. 45 to 48 would be add 3. 84 to 87 would be add 3. Add 3. Okay, so from the looks here, it looks like you're adding 3 and then you're switching the digits around. Then adding 3 and switching the digits. Adding 3, switching the digits, and so on. So if I was to continue the pattern, the next one would be 18 plus 3 is 21. And then 12. And then I would add 3 again. They'd put a 15. And you can see that this is a repeating sequence. I'm back to where I started. Okay, well, let's take a special case. This is one of the more famous sequences, and let's see if we can figure this out. 1, 1, 2, 3, 5, 8, 13, 21. Setting aside these first two numbers, notice that this 2 here is 1 plus 1. And then the 3 is 1 plus 2, which was the two numbers before it. This 5 here would be 2 plus 3, which is the two numbers before it. The 8, if I take the 3 plus 5, I'm at 8. 5 plus 8 gives me 13. 8 plus 13 gives me 21. So this type of pattern, I'm adding the two previous numbers. So continuing this, the next one should be 13 plus 21, or 34. And then this one here should be 21 plus 34, or 55. And this last one here, 34 plus 55, would be 89. Now this type of sequence has a special name, and it's called the Fibonacci sequence. So a Fibonacci sequence is a sequence in which each term, after the first two, is the sum of the previous two terms. So there's some examples there. We've already looked at the first one, but if I go 2 plus 4, that gives me 6. 4 plus 6 is 10. 6 plus 10 is 16. I can also go 5 plus negative 4 is 1. Negative 4 plus 1 is negative 3. Negative 3, or 1 plus negative 3 is negative 2, and so on. So 7 plus 2 is 9. 2 plus 9 is 11. 9 plus 11 is 20. Then 11 plus 20 is 31. 20 plus 31 is 51. 11 plus negative 6 is 5. Negative 6 plus 5 is negative 1. 5 plus negative 1 is 4. Negative 1 plus 4 is 3. 4 plus 3 is 7. So on. All right. The 19th and 21st Fibonacci numbers are 4,181 and 10,146. So what is the 20th? Well, again, the way Fibonacci works is you take like the 19th number plus the 20th number. That's going to give you the 21st number. So if you take two numbers in a sequence, that's going to add up to the next number in that sequence. So if we're told that the 19th is 4,181 and the 20th is whatever it is, we know that's 10,946, then I would subtract. And that would tell me that the 20th number is, it looks like 6 minus 1 is 5. 14 minus 8 is 6. 8 minus 1 is 7. 10 minus 4 is 6. So the 20th Fibonacci number had to have been 6,765. Okay. Now, try to figure out the next three terms and identify as arithmetic, geometric, Fibonacci, or other. It looks like, see here, 1. If I go plus 1 plus, see here, 1 plus 2 would be 3, plus 2 is 6. That doesn't work. If I tried thinking of this as geometric, that'd be times 3. And then times 3, that won't work. So if I think Fibonacci, 1 plus 3, that does not equal 6 either. So this is neither. Or this is other. I guess let's say this one is other. But see if we can figure out the pattern. 1, 3, 6. Clear that off. Well, what is going on? To get from 1 to 3, that would be add 2. And then 3 to 6 would be add 3. Then 6 to 10 would be add 4. Then add 5. Then add 6 to get to 21. Add 7 to get to 28. So it looks like I'm adding by larger and larger amounts. So if I add 8, that'd be 36. Add 9, that'd be 45. And then add 10, that would be 55. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. This is arithmetic. 2, 4, 8, 16, 32, 64. It would be 128, 256, 512. This is geometric, where you're multiplying by 2 every time. And then see here, 7 plus 3 is 10. 3 plus 10 is 13. 13 plus 23 is 36. 23 plus 36 is 59. 36 plus 59 is 9. This is Fibonacci. So 59 plus 95 would be 154. And then 95 plus 154 would be 249. Looks like. Yeah. And then, so I think it's 403 is the last one. 39, 403.